Hey, well, good morning. Here's our RG for the day. I'm going to ask you to go ahead and hit pause while you work through this on your own, and when you've got your answer worked out, go ahead and resume the video. All right. Well, I assume that you've finished answering the do now. Let's take a look for number A, the sides that are given based on the relative angle that's assigned there. We get the hypotenuse, the opposite sides, so opposite and hypotenuse. That comes from the sine ratio. And for B, if we're working from this angle that has been assigned as a reference point, then we've got the opposite side over here is at 2.6. Adjacent side is at 6.1. Opposite and adjacent come together to form the tangent ratio. Well, there's a third question here. Again, go ahead and hit pause on the video while you figure out what you want for your answer. When you're ready, go ahead and hit resume. All right, well, so this time we're given access to a trigonometry table and asked to find which angle would give a cosine ratio of 0.4540. So what we need to do is look down the cosine column until we can find that ratio of 0.4540 and find which is the angle that gave it to us. So 63 degrees in this case. Hey, well, so we're going to today use trigonometry to do some different things that we've done before. We're going to look at how we can find angles if we are given side lengths. So we've got these same three trig ratios that we're using. We've got sine, that's the opposite on the hypotenuse sides. They give us the ratio. Cosine is adjacent over the hypotenuse, tangent is the opposite over the adjacent. And of course, those names come from the sides. The ratios come from the side names, opposite, adjacent, hypotenuse. The opposite and adjacent, we have to remember, those are relative terms. So if we're given the same picture but asked to use different angles as a reference point, the opposite and adjacent are going to switch locations. So I think it is important for us to remember that there's nothing magical about trigonometry. I mean, it's really powerful, and sometimes it seems like magic, but it's just ratios of side lengths. Every triangle with a certain angle is going to always make the same side length ratios. The different possible ratios that can be created by those different sides of the triangle have just been given names. They're Greek, that's weird, but sine, cosine, and tangent just refer to certain ratios of sides. They're just different combinations of sides. All of those things have been measured over the years and recorded in tables. Typically, we don't use tables. We're going to use our calculator most of the time, but I think this visual representation is super important just to understand what's going on. This is not some kind of like magical button pushing on calculators, and a lot of times that's the way we tend to think about things we don't really understand. So I'm going to refer back to this table a couple of times because I think it gives us just a better sense of really what is going on. So let's look at an example to start off with. We've got a triangle here. We've given two side lengths. I've got a side that's 10, another side that's 18. We're asked to find the measure of angle A. So if working from that reference point of angle A, I'm going to determine what are the side names. So I got the hypotenuse here. That's the 18 side. I know that because it's directly across the triangle from the right angle. And working from angle A, the 10 side is the opposite side. I apologize for my handwriting. That looks terrible. So I got the opposite side that is given to me, the hypotenuse. I'm going to use some ratio that combines opposite and hypotenuse. So the second thing I got to determine here is what is the ratio that uses the opposite and the hypotenuse. Okay, so that is always going to be sine. I'm going to use this funny, it's a Greek letter, theta. I'm going to use that symbol just to represent the angle. Normally, that is what mathematicians use to represent an angle. Is a special variable. Like if we're doing algebra problems, typically we solve for x. When we're assigning an unknown for an angle, typically we use theta. We don't have to. It's not like written in stone or anything. So if we wanted to, we could just call this sine of angle A, since that is what is in the problem. And then I'm going to replace those side names with the numbers that I'm given. So the opposite side is 10. The hypotenuse has a length of 18. So this represents the sine of angle A, which I do not know how many degrees that is, but if I knew the number of degrees, then the problem would be done. That's what I'm after. But the sine ratio of angle A is going to be the same thing as 10 divided by 18. Right? That's what this equation is telling me. So if I were to divide the 10 and the 18 to get that decimal form, I'd be able to look it up in the table. So 10 divided by 18. Oops, faster than my calculator. 10 divided by 18. So 0.55555, repeating. Okay, 4 decimal places will be more than sufficient. So what I would need to do in this case is one of two things: either use the table or the calculator to find out what angle measure, how many degrees, will give me a sine ratio of 0.55555. So if I go back to this table, sine is the first column here. I just have to scroll down 0.0s, 0.1s, 0.2s, 0.3s until I'm finding the closest I can possibly get. So this is not going to give me an exact match, but 0.5592 is as close as I can possibly get with the numbers that are in this table. So probably the actual answer is going to be right between 33 and 34 degrees, probably a little bit closer to 34 degrees. But if I were using the table, I would have to say 34 degrees is my closest possible answer. Right. I don't have to use a table because I do have a calculator. So here's what I would do to find the same answer on a calculator. I'm going to use not the sine button, because that's what we hit if we know what the angle is. We're trying to find out what is the sine ratio. So I'm going to do what is called inverse sine. It's like the reverse process, like we just did in the table. Instead of going to the number of degrees and getting the decimal number, it's like telling the calculator, look, you got the decimal number. I want you to figure out where in the table those degrees are. So I have to hit second or shift on your calculator. Calculator's not all the same, but probably is going to be like a second or a shift button. And then we're going to hit the sine button. You see the blue right above it up here, if you can read that, is sine with a little -1 above it. It's just the symbol that means inverse. So I'm going to do the reverse process of what we have been doing in the past. And then I'm going to type in that decimal I just got, my previous answer, and it's going to tell me the number of degrees. I got 33.7 or something like that. So it's right between 33 and 34, like I guessed from the table, probably a little bit closer to 34 based on the 33.7. And I'll just go ahead and write that down on the other screen here as my final answer. So 33.7490. 33.74.90 degrees. We probably don't need 4 decimal places all the time, but we'll have to check what the directions ask us for. In this case, the directions didn't specify, so I'm just going to go with 4 decimal places. All right, let's do another one just for good measure. So here's a completely different triangle. I'm again asked to find the measure of angle A. I'm given the side lengths based on my relative location from angle A. The 9 side, that's going to be the opposite. 15, that is the adjacent. There is also a hypotenuse. Side CA would be the hypotenuse. I don't need that. I also don't know anything about it, so it would be kind of silly to use it. All right, so I got to name the sides first. Now that I've done that, determine which trig ratio uses the opposite and the adjacent sides. So that'll be tangent. I'm just going to skip straight to the labeling this with what's in the problem. So the tangent of angle A is going to be the opposite side over the adjacent. I'm going to fill in those numbers. So 9 for the opposite side, 15 for the adjacent side. I'm going to go ahead and divide 9 divided by 15. Pull up this calculator. I don't need the previous work. 9 divided by 15. So that's 0.6. And then I'm going to continue to explain this in 2 different ways. So what this is telling me is that the tangent of angle A, however many degrees angle A is, if I look in the tangent column on that table, I want to know what angle would give me 0.6. So I go back to the table. Tangent is this third column, and I want 0.6. So I got 0.0s, 0.1s, 0.2, 0.3, 0.4. I just have to scroll down here, and the 0.6009 comes at 31 degrees. So let's say it's right about 31 degrees. It'd be a teeny bit different than that. So if I do this on my calculator, I would guess probably it's going to be like 30.9 degrees, something like that. We'll find out in just a minute. But this is what I'm you're going to find by using a table. I just need to get as close as possible in that tangent column, and then that came from 31 degrees is the closest I've got. Okay, so let's do the same thing on the calculator. I'm going to write this down before I type it on the calculator screen. So what I'm doing here is the inverse tangent with a little -1 above it. That's called inverse tangent. The reverse process, right? And this is what I'm going to type into my calculator, the inverse tangent of 0.6, and that's going to tell me what is angle A. Right. So on my calculator, I'm going to hit second, and then tangent. It's going to give me this little blue thing right above it, inverse tangent. There it is. And then I could either hit, to use the previous answer, I could just type in 0.6. We could do the same thing either way, but we'll make it match what I just wrote down. Hit enter, and just as I guessed, 30.9 for the number of degrees. So 30.9638. If I was going to round to 4 decimal places, 7. I have to round it up because the next number after that's a 5, and 5 means I got to round up. So 30.9638. 30.9638 degrees. All right. That's pretty much, that is the process. I'll do one more just for good measure, as you've got a chance to see this happen one more time. So again, same directions, find the measure of angle A. And I'm given some side lengths. So based on the relative location of angle A, the 32 side, that's the adjacent, and the 45, that is the hypotenuse. Oops, my Y got lost. So I need to know where is the right angle. So that's how I'm going to find the hypotenuse. Straight across the triangle is always going to be the hypotenuse. And then my little stick person standing at angle A, there are 2 sides of the triangle that come together at the angle where my stick person is standing. One of them is the hypotenuse in this case, and the other one is always going to be adjacent. That just means the side that is right next to me, or it's got to be one of the 2 sides comes together to form that angle. Okay, so I named the sides. Next, I need to determine which is the trig ratio that uses those 2 sides. So hypotenuse and adjacent is going to come from cosine. Cosine is always the adjacent on the top of the fraction and the hypotenuse on the bottom. Okay, so that's what the just kind of the ratio looks like. I'm going to put in the numbers from the problem. So the cosine of angle A, the adjacent side was 32, the hypotenuse is 45, and I will go ahead and divide 32 divided by 45 to find what is the decimal version of that. 32 divided by 45, that's 0.7111111. Just keep track of that. Just go with 4 decimal places for now. And then what I want to find out is not the cosine of angle A. Right? I want to find out what's angle A. So to get angle A, I would need to do the inverse cosine of this decimal I just got, 0.71111. Right? And so I'm going to go to the calculator now, and second cosine, so there's my inverse cosine function. I can see it right there, and then I'll just type in that same decimal, 0.7111. Close the parentheses, and that's going to be 44.6755. All right, we'll go ahead and write that down, 44.6755. What? Shoot, my memory's failing me. Oh yeah, good job. All right. And I skipped over this part, or did it in the reverse order. So I've used my calculator first. That's usually what we're going to do. Calculators are, a lot more handy than a trig table. We don't often have trig tables with us. But to do the same thing on the trig table, I would go to the trig table and find where the cosine value in that column of cosine is 0.7111. So here's my table. Cosine is this middle column, and you start off with 0.9s, and then they get smaller, 0.8s, 0.7s, and there's not an exact match here for 0.71111, but it's going to be between these two. So I got 0.7193, which seems like it's pretty close, but I think actually 0.7071 is going to be closer. At any rate, it's going to be between those two numbers, right? So it's going to be between 44 and 45 degrees, and would so 45 is a little bit closer, but we'd say probably it's going to be like 44.5 degrees, right? If I was only using the table, I'd say it's got to be like, right in the middle of them. Of course, we already did it on our calculator, so we know what it is, but the table is saying the same thing. We just get a higher level of precision by using our calculator because it's not constrained to only having the values of whole number degrees. So there, just for comparison's sake, the thing we got from the calculator is in fact about halfway between 44 and 45 degrees, but the calculator was able to give us a better answer than guessing from the table.